There's still a lot of confusion about it, whether or not it's the well, I haven't heard it referred to as the God particle since it was first discovered, but where does the Higgs boson fit into fine tuning? And here it might do to have a bit more background on what it is. We can't take it for granted the same way we might a proton or an electron.
Yeah, so the Higgs particle is, as I said, is just one of the particles of the Standard Model. And the important aspect is not necessarily the Higgs particle itself, but the fact that the existence of the Higgs means that there is a Higgs field through the universe. So in modern quantum physics, everything's fields, right? So we have like an electron field through the universe, and a ripple in that field is the electron. So you put ripples in the electron field, you get experiments that see electrons. So we have the Higgs field, and a ripple in the Higgs field gives us the Higgs particle, which we see at CERN. But the field has a particular property, and what that means is that other particles take notice of the existence of the Higgs field. So there's a coupling between them, and that taking notice of the Higgs field, right, it is manifested as the mass of the particles. Okay, so the electron wiggle in the electron field, that wiggle senses the Higgs field, and the sort of reaction between the two sets the mass of the electron. And what we mean by mass there, of course, is essentially, how hard do you have to push on an electron to get it to accelerate? Okay, it's that kind of quantity that we're dealing with. And so various particles have various kinds of couplings to the Higgs field. So the electron coupling is relatively weak, so the electron has a small mass. The quark couplings are slightly bigger, but not a lot bigger. So, that gives the quarks their mass inside the protons and neutrons. The photon, it doesn't interact with the Higgs field at all, so it is massless. And then there's a few other particles, the W and the Z particle. They have a bigger interaction with the Higgs field, and so they're quite chunky particles. So the Higgs field, right, has this coupling to it, but it has this energy throughout the universe, and that energy is one of those things that we don't quite understand why it is the value that it is. And so again, that it could be anywhere in a potential range. Of course, if we take the Higgs field down to zero, so it's such that it's there but has zero everywhere, then that means that no matter what the coupling is between the particles, they don't get any mass. So without the Higgs field, everything is massless and zips around at the speed of light. And then when you wind the Higgs field up, you can make particles more and more massive. And you can adjust the couplings of each of the particles as well. So you can change how much mass there is. So the Higgs plays a very important role in physics, in that it gives the fundamental particles their mass, and it sets some sort of scale, but we don't understand why it quite has the energy that it does. And of course, there are other questions about whether or not the Higgs field is related to some of the other mysterious fields we have in the universe. People have suggested that maybe the Higgs field is related to this dark energy stuff that we see accelerate in the universe, that somehow there is a relationship between the two. Again, nobody's really tied that down, but it's what people are looking at. So yeah, if we didn't have the Higgs mechanism and the Higgs field, particles wouldn't get any mass, and we would live in a very different kind of universe, right? We don't even really know how to understand some of these questions, right? If the electron was massless, how would it interact with atoms, right? So if you think about it, a proton, which is made of 3 quarks, most of the mass of the proton doesn't come from the masses of the quarks in there. So you could make them massless and you can still end up with a massive proton because the mass comes from the energy of all the other things going on inside the proton. So you could build a proton, and it would be a slightly different mass if you make the quarks massless. But if the electron doesn't have any mass, so it moves like a particle of light, but it still has charge, will it ever get captured by atoms? Will we ever get, neutral atoms in the universe where we have a massless electron? So again, it would be a very different universe if we didn't have the Higgs field. Some things would look similar, but other things would look radically different.
So whenever we're talking about altering the masses of the up quark or the down quark or the electron, what we're really talking about is their coupling with the Higgs field. So the Higgs field is, even though we hadn't been talking about it before 5 minutes ago, it's extremely relevant to pretty much everything we've already discussed, even if it hasn't been named.
Yeah. Yes. Yeah. Look, it definitely does play a key role. But again, there are other complications in there, right? Because as well as there being the Higgs field, there are the couplings between the Higgs field and the particle fields, etc. So it's a bit messier, but yeah, the Higgs plays a pretty central role.